Did you ever imagine this is how a fire could actually look like? Or like this? Probably not. However, curiosity brought you here because you've probably done it 1,000 times. Struck a match, watched the tiny flame bloom, felt the sudden heat on your fingertips, and then just stared. That little dancing glow has warmed us, cooked our food, scared away the dark, and terrified us when it got out of control.
Get more pressure! It's stuck! The pressure's too high! Hold it steady! We can't let it spread!
Yet almost nobody stops to ask the one question that turns the everyday miracle into something mind-blowing. What is fire actually made of? Is it alive? Is it a thing? Or is it something wilder, an invisible chemical riot, happening right in front of our eyes? However, we are about to answer these questions. By the time we're done, you'll never look at a candle, a bonfire, or even your gas stove the same way again. The answers get surprisingly technical, a little dangerous, and completely fascinating. Stick with me all the way through because the payoff is huge. However, before we continue, permit me welcome you to the channel, and yes, we know curiosity brought you here. This space satisfies that curiosity by exploring the strange, forgotten, misunderstood, and deeply human tales found in history, science, and the lives of real people. If this sounds like something you'd enjoy, then consider subscribing to the channel for regular videos that will always leave you nodding your head after watching. Now let's move on to the story. Let's begin by clearing up a common misconception. Just so you know, fire isn't a physical thing. You can't put it in a jar, bottle it, or weigh it like water or sand. Instead, fire is a process, a fast, ongoing chemical reaction called combustion. The glow we see in a flame is just the visible light made by this reaction. It's like a rainbow. You can't touch a rainbow because it's just light bending through water. Similarly, you can't truly hold fire. It's the light, heat, and energy released as matter transforms dramatically from one state to another. For a fire to begin and continue burning, 3 elements must be present, forming what is known as the fire triangle: fuel, oxygen, and heat. Fuel refers to any material that can burn, such as wood, paper, gasoline, cooking oil, or even magnesium metal. Oxygen typically comes from the surrounding air, which contains about 21% oxygen. Heat provides the initial spark needed to start the fire, whether it's from a match, friction, lightning, or in certain conditions, spontaneous combustion. If any one of these 3 elements is removed, the fire will extinguish. This is why blowing out birthday candles works. It removes oxygen and cools the flame. Why water can put out a campfire: it cools the heat and can also reduce oxygen. And why placing a lid on a grease fire is effective: it cuts off the oxygen supply. However, modern fire science has updated this idea to the fire tetrahedron, which includes a 4th element: the chemical chain reaction. Once a fire starts, unstable and highly reactive molecules called free radicals keep the reaction going, much like a line of falling dominoes. If you break this chain, using certain extinguishers like halon or dry chemicals, the fire will stop, even if the other 3 elements are still there. This explains why some fire suppressants work so well. They don't just cool or cut off oxygen, but they chemically break the cycle. Now, let's explore the amazing process that makes a flame dance and shine. Picture a big log burning brightly. The very hot fire starts a process called pyrolysis. In this important first step, the solid wood breaks down into simpler gases without actually burning. Wood is mostly made of cellulose, which is a complex sugar. It releases many different gases, including light hydrocarbons, water vapor, carbon monoxide, and carbon dioxide. These new, very hot gases are lighter than the air around them, so they rise up and mix with oxygen. This mixing causes a strong chemical reaction that creates a lot of heat. The fuel gases combine with the oxygen, making more carbon dioxide, more water vapor, and a burst of powerful energy that we see as heat and bright light. The flickering flame we see is really just a dynamic dance of super hot gases, each one full of excited energy. Look at a candle flame, for example, and you'll see its warm, yellow-orange light. This color mostly comes from countless tiny soot particles, which are essentially small, unburned bits of carbon. These tiny particles get incredibly hot and glow brightly, like many small glowing coals filling the air with their fiery light. On the other hand, a clean-burning flame, such as one from a butane lighter, an alcohol burner, or a kitchen gas stove, usually appears as a beautiful blue. This blue color shows that the fuel is burning almost perfectly, with very little soot left over. The blue light comes from highly energetic gas molecules, especially tiny chemical pieces called CH radicals. These energetic particles create light directly through a process called chemiluminescence, which doesn't need solid, glowing bits to make light. Blue flames are much hotter, often reaching intense temperatures from 1,400 to 1,600 degrees Celsius, clearly showing very efficient burning due to a lot of oxygen. This allows for a thorough and complete burning process. The different colors of a flame act like a secret code, showing what is burning and how hot it is. Also, many chemical elements glow with their own special colors when they get very hot. For example, sodium glows a bright yellow, which is why it's used in street lamps. Copper compounds glow a beautiful green or blue-green, like you see in fireworks or when old pennies are heated. Strontium glows a deep red. Potassium gives off a soft violet or lilac, and calcium burns with a bright orange-red flame. It is interesting to note that some people often claim that fire is plasma, which is the fourth state of matter alongside solids, liquids, and gases. While there's a kernel of truth to this, the situation is more complex. Plasma is essentially an ionized gas, meaning atoms have lost electrons, forming charged particles that can conduct electricity and react to magnetic fields. In very hot flames, such as those found in welding arcs, 3,000 to 6,000 degrees Celsius, lightning or acetylene torches, a significant amount of ionization happens, creating genuine plasma. However, a typical candle flame, which burns at around 800 to 1,400 degrees Celsius, is only weakly ionized, perhaps 0.01% or even less. It's mostly hot gas with just a tiny bit of plasma mixed in. Therefore, while fire can contain plasma under extreme conditions, everyday flames are more accurately described as glowing, reacting gases that include bright soot particles. At this point, someone might ask, but why does fire shimmer and sway instead of staying put like an LED light? Well, unlike LED lights, fire is extremely sensitive to everything around it. Hot gases are lighter than cool air, so they shoot upwards quickly. Cooler air then rushes in from the sides and bottom to fill that space, creating a constant movement of air. Even tiny changes in air currents, how fuel vapor escapes, and the room's temperature all cause the fire to churn and swirl. This is why a candle flame flickers near an open window, or why campfires jump and twist in the wind. When the air is still, flames are steadier, but they never stay perfectly still because fire is always moving and changing. Another question that does come up most often than usual is this: is fire alive? Because when you come to think of it, fire consumes fuel, like eating, requires oxygen, like breathing, grows and spreads, reproduces by igniting new fuel, and dies when conditions fail. Because of this, people in ancient times often thought fire was a living spirit, mesmerizing and powerful, almost as if it had a mind of its own. But from a scientific view, fire is not alive. It doesn't have cells, DNA, a biological metabolism, or the ability to keep itself stable or change over time like living things do. It doesn't produce young that are different. It just keeps a chemical reaction going. Fire simply follows the rules of physics and chemistry without any purpose or ability to adapt. Still, its lifelike qualities are so striking that scientists sometimes use fire as a special example when trying to define what life is. It's not alive, yet it imitates life so well that it has influenced our stories and fears for thousands of years. Humans have a long and remarkable history with fire. We've been using it in a controlled way for over 1 million years, as shown by burned bones and heated tools found in African caves. Cooking with fire allowed us to get more energy from our food, which in turn led to smaller stomachs and larger brains. Fire was also essential for making tools, clearing land, and keeping us safe at night. It powered major eras like the Bronze Age and the Industrial Revolution, and it still provides most of our energy today. However, fire can also be very destructive, causing wildfires, house fires, and events like the Great Fire of London in 1666, which started in a bakery and destroyed many wooden buildings. By understanding the fire tetrahedron, we can fight fires more effectively. Water cools the heat, foam and carbon dioxide cut off the oxygen, and certain chemicals disrupt the fire's reaction. I know you didn't see this part coming, but imagine fire not as a flickering orange teardrop reaching upwards, but as a perfect, glowing ball, like a tiny sun floating in the dark emptiness of space. This is exactly what happens when fire starts beyond Earth, where there is no gravity. Because hot air doesn't rise in space to create the usual tall flame shapes, the flame instead spreads out evenly in all directions, forming a beautiful, slow-burning ball. These space flames burn their fuel with gentle slowness, often so faint they are almost invisible, like ghosts in the vacuum. Tests on NASA's International Space Station have shown these flames, where heat and fuel spread only through the slow movement of molecules, not by strong air currents. This delicate balance means these ghostly flames often put themselves out, simply disappearing as their fuel runs low, unable to keep burning in such strange conditions. Now also picture yourself in the very deep parts of the ocean, a place where you might think fire could never exist. Yet even in this watery world, fire manages to show its powerful presence. The life-giving oxygen that typically fuels fires on land isn't taken from the air. Instead, it's cleverly pulled from special chemicals, or from metals that react strongly with water. Imagine the sudden, bright burst of a magnesium flare, a brilliant burning light piercing the deep darkness of the ocean. This intense fire is fueled by the very water around it. This isn't a gentle campfire glow, but a powerful, almost defiant show of heat and light. Fire, at its core, is an amazing shapeshifter, a changing force that either adapts to the most unlikely places, changing its basic nature to survive, or when conditions are truly impossible, it simply stops existing, disappearing into nothingness. So, what truly is fire? This amazing, destructive, and life-giving event. In its most basic form, it is the bright light coming from atoms that are very excited and full of energy. It is the strong heat that appears when chemical connections are violently broken. It is a powerful burst of pure energy, released with great force as molecules, once neatly arranged, eagerly form new patterns. Think of it as a beautiful yet wild dance of extremely hot gases, swirling and twisting in a complex, ongoing loop of chemical reactions that feed themselves. Fire is not something you can hold. It is not a solid thing that exists on its own. Instead, it is a lively, stunning change, a furious process happening in an instant, right before your eyes. This ancient dance is as old as the first breath of oxygen in our planet's early air, yet it feels as familiar as the quick spark from your next match. Thanks for watching! If you have ideas for our next video, please share them in the comments and we'll definitely attend to them. Thank you also for joining us on this journey of curiosity. Remember to like this video, subscribe to our channel, and keep an eye out for more eye-opening videos.